What's going on, you guys? So today we're going to do count primes. And so the idea behind this is we're going to count the number of prime numbers less than a negative number or a non-negative number n. So for example, 10, that would produce 4 because there are 4 prime numbers less than 10. So a prime number has two factors, 1 and itself. So 2, it's 1 and 2, 3, 1 and 3, and so on and so forth for 5 and 7. Like 9, for example, is 3 and 3. So it has more than just those two, its original two factors, so it is not a prime number. So, okay, let's think of a brute force way that we could solve this. So, brute force, you say, for each number we could find its factors, and if it has more than two factors, 1 in itself, then we'll say it is not prime, and prime otherwise. So how would we do that? We would do for I in, so it looks like we're returning 0 for 1 and 0. For I in 2 until n, so that goes up to n minus 1. If get factors I, that would be another function we'd make, and if the size of that is greater than 2, well, we'd have, okay, so we'll create a primes variable, set it to 0. We'll say if it equals 2, we'll increment primes, and then afterwards we can just return primes. And then our get factors function would look something like get factors. It would take an integer and it would return like a list of integers. And how do you get the factors for some number? You'd say, let's think. So factors would just equal a list, and would start off with 1 and n, and so for I in 2 until n, how do we know if a number is a factor? If we divide a number, so if we divide 4 by 2, the remainder is 0. So we know that 2 is a factor of 4. So we can use that fact here. We can say if n modulus I is 0, then we want to add factors. We want to add I as a factor. We want to add I as a factor, and so this would be a recursive function. So so let's think about it. So $20, right? So its factors equals 2 times 10. So our for loop, we would start at 2. So we would say 20 modulus 2, does that equal 0? Yes. Okay, so we want to add 2, and we also want to add what? We want to recursively call get factors on n divided by I. So in this case, 20 divided by 2, 10. So we're going to call get factors on 10. So we go back into get factors. We see is 10 divisible by 2? Yes. Okay, so we're going to add 2, and we're going to call get factors on 5. And so it would just be this recursive function. And then we would return factors. We would make this a set. Let's call it like a set. because we don't want to have duplicate values inside here because we're counting them up here. So this would be a set of integers. So what's the problem with this approach? So first of all, let's think about time and space complexity. O of n squared, right? Because our first loop goes until n. Our second loop is going until n. Yeah, this is O of n squared. And space complexity, we have all these recursive calls to get factors. So O of n space complexity. O of, well, I mean, it's being divided by a number. So maybe that's O of log n. But still more than O of 1, which is what we can normally find. Yeah, if you guys have any comments on space complexity of this brute force, let me know. Okay, and then there's a way, so what's the problem with this one? We are going to find the factors, so we're going to loop through this get factors function, and we're going to find the factors of, like, say n is 8. We're going to find the factors of 4. We're going to find the factors of 8. Well, the problem is when we find the factors of 4, we find that they're 2 and 2. When we go to find the factors of 8, we redo this work here. We've already done it, and so we do it again. So we repeat that work. So that's going to take a lot of time. So let's think about, so there's actually a famous algorithm that we can use that will help us avoid repeating that work. So it's called the sieve of Eratosthenes. It's pretty cool. Go ahead and, if you have time, just pop that into YouTube and check out the first video. It's a pretty good explanation if this one doesn't make sense here. So basically what we're going to do is we're going to create an array. We're going to create an array from 0, 1, 2, all the way to n minus 1. And we're going to set all of its values equal to 1. We're going to say initially all values are prime. Then we're going to loop through each element of the array, and since each element is prime, we're going to, we know that it's multiples of, let's think, its multiples are not prime, right? So if 2 is prime, then 2 times 2 is not prime, and 2 times 3 is not prime, right? Because 6, oh, so 2 is prime, but a multiple of 2, so for example 3 is not prime because it has more than itself and 1 as factors. So what we're doing is we're setting all multiples of prime numbers to not prime. So initially we have an array of just a bunch of 1s, right? We're saying everything is prime. And then we set, let's see, 2, 3, 4. So we get to 2, right? So this will be 0 and this will be 0 because of these here. We'll get to 2. Okay, 2 is prime. So now let's set all of 2's factors to not prime. So 3, 4, okay, we're setting 4 to 0. And then 5, and then 6, we're setting it to 0. And then 7, and 8, we're setting it to 0. So we do that through the whole thing. And so that's eliminating that extra work that we're doing here. So one time we figure out, okay, 2 is a prime number. Let's set all multiples, so including 4, 6, 8. Let's set all of them to not prime. So how can we do that in code? Let's think. So we'll create an int array. It's primes of size n, and we'll initialize all all of its values to 1. So we'll loop over all the values of primes starting at 2, and if that value is prime, so if primes I equals 1, we're going to set its multiples to 0 or not prime. And how are we going to do that? We're going to create a new variable j. We're going to say while I times j is less than n. So for example, if n equals 10, we're going to loop from 2 until 2 to 9. And we're going to start at 2. We're going to say 2 times 2 is not prime. 2 times 3 is not prime. 2 times 4, 2 times 5, all the way up to, I guess it would stop at 5, right? Because 2 times 5, 10 is not less than 10. Okay, we're going to set primes of I times j equal to 0, and we're going to increment j on each run through this loop. So just add a plus plus there. And then at the end, we can just return primes.sum. And so this is eliminating all the duplicate work. So let's think about space and time complexity. All right, so at least n for this first loop. In this second loop, so it's starting at 2. So in this case, so for 10, we only get up to j equals 5. So that's something like a log n. So it's something like n log n here. So a little bit better than our initial one. And I say that because even though our n is 5, we went from 2, we did 2 times 2, 2 times 3, 2 times 4, 2 times 5. So our inner loop only got called 4 times, even though n is 10. Okay, yeah. So if you guys have anything different on time complexity and log n, let me know. Time complexity and space complexity. It's going to be just O of 1. So there's no recursive function calls. We are storing primes. So if you get a really big number, if you say, max integer value, this is going to be a big integer array we're storing. So let me know if you guys think that's O of n space complexity, but I think that's O of 1. All right, let's translate this to Kotlin here. Okay, just adding our punctuation. All right, let's see if that works. Oops, that did not work. Let's think about why that did not work. So 10, let's work through this and see if we can figure this out. So 0, 1, we need to, here's the problem. We didn't set 0 equal to 0 and 1 equal to 0. So that added two additional values to our primes array. Oh, and then what if, so we need to think about edge cases. So if n equals 0, we're going to return 0. If n equals 1, we're also going to return 0. Okay. Okay, you guys, so we made a bit of an improvement on the brute force technique. We're doing n log n, time complexity, O1 space complexity, and this is the sieve of Eratosthenes. All right, stay tuned for the next.